So in this video, I'm going to show how you could tether your Raspberry Pi to your Android phone so you can have internet when you're away from Wi-Fi or from your home. I'll be using my Galaxy Nexus. As long as you have tethering working, USB tethering working on a normal computer, it should work just fine on the Raspberry Pi without installing anything or changing anything. So let me set everything up. So once you have your Pi booted up, you just plug in your phone to the USB, and then you turn on USB tethering on the phone itself. So and that's that for the phone. On the Raspberry Pi, if you do ifconfig, you should see USB 0, if you could see that. And that means it detected the phone. So all you're supposed to do is run sudo client USB 0. Sometimes it's fast and sometimes it's not. So that's done. So now ifconfig gives me an IP address. I could ping google.com, and let's see if I could do the browser. And it works. Just using my phone over LTE. So that's it.
Do is I'm going to take my LDR here, my light dependent resistor, and I'm going to place this in the breadboard. I'm going to place it over here, and I'm going to put one leg into row 1 and one leg into row 3, like that. And then I'm going to take a 1 microfarad capacitor here, and I'm going to place the long leg of my capacitor into row 3 and the short leg into row 5, so it's in series with the light dependent resistor. So when current flows through the capacitor, it's going to have to flow through the light dependent resistor first. I want current to flow through the LDR and the capacitor. So on row 1, I'm going to place a jumper lead, and that's going to go into the 3 volt output on my Pi there. And then from the capacitor's short leg, that's in row 5, I'm going to run that into any ground pin. So I'm just going to pick this one here, like that. And the last thing to do is to come from row 3 here on the breadboard and run that out to one of my GPIO pins. So I'm going to choose GPIO 4, which is this one here. Now we can go and encode this and see if we can detect some light. To get started, I'm going to come to my menu, come down to programming, and then choose Python 3 idle from the menu. So my interpreter's opened up. Just resize this a little bit. And then I want File, New File. Now we have the window to run my programming. So we're going to start off by importing the GPIO0 library, and we want the light sensor from that library. So we'll go from GPIO0 import light sensor. Next, we want to tell the we need to set up our light sensor. So I'm going to say LDR equals light sensor 4. Now I can go ahead and save and run my code. So we'll file, save as, we'll call it ldr.py, save it, and now I'm going to run it by hitting F5. Now I'm going to run it by coming up, run module. Now I'm going to shift over into my interpreter and see what readings I'm getting from my LDR now. So if I type ldr.value, it comes back and tells me there's a value of 0.86 at the moment. What I'm going to do now is I'm going to shine my laser onto the LDR and find out what the value is this time. So here we go with the laser on the LDR, and I get a value of 0.92. So there's not much differentiating those two values at the moment because my LDR's in the light just in the room that I'm in. So we need a method just to reduce the amount of light that's getting to my LDR. To try and get my LDR to detect 0 light or very little light at normal levels, I'm just going to cover it up. So what I've done here is I've taken a length of a drinking straw, and I'm just going to pull my LDR out of the breadboard, and then I'm going to insert the LDR into the tip of the straw, like that. Give it a bit of a push in. So now my LDR is covered up and it should receive a little bit less light from the sides. I can now place it back where it was before. So it's in rows 1 and 3. Like so. And now I can run my code again and see whether I get different light levels when the LDR is being illuminated by the laser and when it's not being illuminated by the laser. So let's see what happens now. I'll do ldr.value again, now that the straw's over. And I get a much lower value because less light is getting to the LDR, which is changing its resistance. I'll now shine my laser down through the straw. And we're back up at that 0.9 sort of level. What I'm going to do now is I'm going to add a buzzer into my circuit so when the light beam gets broken, the buzzer will sound. So I'm going to take a buzzer here and I'm just going to place this into my breadboard. And I'm going to place it on row 15, so that's the long leg into 15, which means the short leg is going into 18 here. And now I'm going to take a couple of jumper leads, go from 15 there into one of my GPIO pins, and I'm going to choose pin 17 from 18 here into another ground pin. There we go. Now we can go back to our Python script and we can include the buzzer in our program. So we want to start off by importing the buzzer as well. So go up to my first line here and I'm going to put a comma in and then type buzzer. And the first thing I want to do is I want to test that my buzzer's working. So down here, I'm just going to say buzzer equals buzzer, then tell it which pin it's on. I put it on pin 17. So I'm just going to save and run this again so I can test that my buzzer's working. Save and run module. And then over here in the interpreter, I should be able to just type buzzer.on and buzzer.off. So to code this to include my buzzer, the first thing I need to do is grab the sleep from time. From time, import sleep. Those two lines stay the same. Now I'm going to start up an infinite loop. So while true. Now, if I just constantly ask what the LDR values are, they're going to shift all over the place because the program's going to be asking at such a high rate because it's going to run so quickly. So I'm going to actually slow my program down a little bit by putting a sleep. And we'll go for 0.1 seconds. Then if the LDR value, and we'll say if it drops below, let's go for 0.5. So if the LDR value, the reading of the LDR ever drops below 0.5, we can turn our buzzer on. Buzzer.on. And if it's above 0.5, we'll turn our buzzer off. And there we go. So that's my completed program. Now we're going to see whether this works. So I'm just going to save it. So here we go. I'm going to run my program. And the buzzer comes on. Now if I shine my laser down through the torch, we can see the buzzer goes off, and every time I cover it up with my finger, the buzzer comes back on again. So we have the basic laser tripwire working now. We just want to package it in a slightly better container. LDR, and my capacitor out of the breadboard now. I'm now going to connect them together by taking my capacitor, taking the long leg and one of the legs of the LDR and placing them into the same end of a female to female header cable, just like that. Now I want to tape them together a little bit just to keep them secure. So I'm just going to wrap a little bit of tape over the header lead and over the legs of my components. And there we go. Now I can take two more female to female header cables, and one's going to go onto the leg of the LDR and the other one onto the other leg of the capacitor. And now I need to just wire up my buzzer. So same with the buzzer. I take my buzzer and I get a female to female header cable and place on one leg, and then another female to female header cable and place that on the other leg, like so. And I'm good to connect it all up to the Pi. So the LDR capacitor combination, that leg of the LDR, I'm going to place that into my 3 volt there. The middle jumper lead, that one's going to go into pin 4. So 1, 2, 3, 4. So that's in GPIO 4. And then that final one into one of my ground pins. So I'm going to put that back into this ground pin just there. And then for the buzzer here, so the long leg, that is to go into GPIO 17. So 4 ground 17 is just there. And this one into one of the ground pins, one next to it there. Okay, so now that's all wired up and I'm ready to put it in its housing. Just a plastic box. Okay, and I've taken my Raspberry Pi and I've connected it to a battery here. Okay, so that's going to run independently, and inside the plastic box I've just put a little hole here, and that's so my straw can poke through that hole just like that, and that's where I can now aim my laser, and I can place the whole lot all under the box like so. And now all I have to do is fire the laser down this hole, and if anything breaks the beam then it should go off. So let's just test this and see whether it works. The laser pointer gaffer taped to the skirting board, and if we look over here I've got my Raspberry Pi sitting in its box with the straw sticking out there and the laser pointer shining into that. If you want to make sure that the laser's there, what we can do is we can turn the lights off, and then we can blow a little bit of flour. We can just about see the laser. There we go. We can turn the lights back on now, and then we can get some unsuspecting person to walk through the laser and set it off. And then when they walk back out again, and we can see whether it works with dogs. Loki, come. Yes, it works fine with dogs as well.
A simply to build machine is the V-plotter shown here. Those machines are also called hanging pen plotter, polar graph or Robot. The working principle is based on a pen that is hanging on 2 cords whose length can be varied by 2 motors. The V-plotter shown here uses a Raspberry Pi, 2 double H bridges to drive the motors, 2 stepper motors used to vary the cord length, and finally 1 servo used to lift or lower the pen. The whole mechanism is mounted on a plate with the dimensions 94 x 20 cm. The plate for the drawing area below is 90 x 43 cm. The area covered by the pen is approximately 56 x 30 cm. The bipolar stepper motor used here has 2 coils and so 4 terminals. With the multimeter switched to continuity, you can figure out what pair of terminals is internally connected to one of the coils. At an operating voltage of 5 volts, 150 mA are running through an enabled coil, while that current is 340 mA at 12 volts. You can't connect a stepper motor directly to the GPIOs of the Raspberry Pi, because those pins provide no more than 2 mA at just 3.3 volts. H-bridges are needed to amplify the power and to swap the polarity at the coils of the stepper motors. The board shown here has 2 H-bridges and so 4 output terminals. Each of the coils of the stepper motor has to be connected to one of the H bridges. 4 GPIOs of the Raspberry Pi have to be connected to the 4 input terminals of the H bridges on the board. 2 stepper motors are needed for the V-plotter, thus 2 double H bridges, and so 8 GPIOs of the Raspberry Pi are used to control the machine. You can get the schematics on the project page. The cord is wrapped around the shaft of the stepper motors. The motors are mounted with their shafts pointing to the base plate to get the cords as closely as possible to the drawing board. A clip is used to connect the pen to a stripe of perforated metal. That metal stripe in turn is connected to a stripe of acrylic plastic. A servo can bend the metal stripe and so lift or lower the pen. The triangular wire strap is used to stabilize the pen during operation. If the pen is lowered, the whole mechanism rests on 3 points on the drawing plane, by what the pen is pulled perpendicularly over the board. A simple way of connecting the pen with the mechanism is using loops at the ends of the cords. In doing so, the pivot axis is congruent with the center point of the pen, thus there is almost no deviation when deflecting the mechanism by hand. The higher the fastening point of the cords, the higher the force on the drawing plane. However, if that fastening point is too high, the pen tilts. Finding the right height is a bit tricky. Here the cords are linked with the mechanism by 2 metal hooks. In doing so, the height doesn't have to be readjusted whenever the pen is replaced, but there is a higher deviation when deflecting the mechanism. You can hang the V-plotter flat on a wall, but a slight deviation from the vertical line causes a higher downforce of the pen, and so a higher precision of the drawings. You have to drive the pen to the point of origin manually before starting a plot. The software needs 4 parameters. The base length, thus the distance between the 2 stepper motors, the length of the 2 cords at the point of origin, and finally the number of steps a motor needs to move the pen for 1 mm. To get that value, one of the motors is turned for 2000 steps and the difference in cord length is metered. Those parameters have to be entered in the source code. The program can process scalable vector graphics. The source code and some explanations about the trigonometry used to transform the cord length into XY coordinates are available on the project page. So let's do some drawings. The machine plots 2 text lines. The first one is at the top of the drawing area. The speed of the stepper motors should not be set too high, or else the cords and so the pen will start vibrating. The accuracy of that low-tech plotter isn't too bad. The characters with a height of approximately 5 mm are easy to read. The second line is placed at the lower end of the paper sheet. In the template file, both text lines are arranged on straight lines, however there is a noticeable deviation at the plotted version. After the file is processed, the pen moves back to the point of origin. Let's plot a square to have a closer look at the deviations. During plotting, the cords are wound respectively unwound by the stepper motors. The cords are wound in multiple layers on the shaft of a motor. Whenever a cord length is short, the diameter of motor shaft plus cord layers is maximal. If a cord length is at its maximum, the diameter of the spool equals the diameter of the motor shaft. As a consequence, the move length of the pen with each step of a motor is lower the longer the chord length becomes by what the calculation done by the software doesn't meet the reality, resulting in a visible error. Another reason for deviations is the flexibility of the chords. I can stretch the chords and so deflect the pen easily by hand. The closer the pen is to the baseline, the higher the forces acting on the chords, and so the larger the deviations caused by the flexibility. That's why the lower text line is almost on a straight line. Don't set the point of origin too high on the board and keep the drawing area small to reduce the deviations and so to get good results with this simple plotter. The deviations are negligible when drawing objects without straight lines or circles. When using 3 templates, one for each pen, you can plot a colored raspberry. To get bold lines, even with a fine pen, the software calculates circles around the paths of the drawing. The plotting takes much longer, but the lines are clearly visible, even from a distance. It's fun watching the plotter drawing objects. With a larger diameter of the spools, the deviations caused by the multiple chord layers are reduced. I am using a gear made with my CNC machine. You can get a detailed description of that machine on the project page. The chords are wound on a ball bearing with an outer diameter of 30mm. With a chord length of approximately 140cm, only some layers are needed to wind the chord on that larger spool. Furthermore, the relative error per chord layer is lower than with a 5mm spool. The painted square has an edge length of 30cm and the quality of the drawing isn't too bad. The drawing board is mounted on a framework made of timber battens, thus there is no need for a wall. This V-plotter has a drawing area of approximately 60 x 85cm. With a large pen, there is no need for drawing circles around the path, which speeds up the plotting of the file. That's all about V-plotters for now. Anything else about that machine is written on the project page. Thanks for watching and I'll be back. In a previous video about physical computing, I have demonstrated how to control peripherals through GPIOs. Now I have written some code lines enabling you to switch the GPIOs of a Raspberry Pi through a very simple browser interface from any place on this planet with internet access. How to install Raspbian on a SD card and get started is described in detail at the homepage of the Foundation. There is no need for the graphical mode, the installation of my software is done from the command line. What you need is an internet connection, so link your Raspberry Pi with your router through a LAN cable. Only 3 commands turn your Raspberry Pi into an Internet of Things device. The first one downloads an installation script. The second command turns this script into an executable file. And the last one starts the script, which does the rest of the installation work. Some questions have to be answered, mainly to set the installation directory and the password. That password is needed to access the Raspberry Pi through the browser interface. Since the password is also used to identify your Raspberry Pi, it should not be as easy as the one I have chosen for this video. There is a step-by-step description available at the project page, giving you a detailed insight in what the installation script does. The source code of my programs is of course also available. There is one tiny C program that enables software controlled pulse width modulation for each GPIO, and another C program that reads the status of the pins if a sensor or a switch is connected to that GPIO. Both programs are called from a Perl script that connects your Raspberry Pi with 2 more scripts running on an internet server. At the end of the installation process, you can choose to start the Perl script on your Raspberry Pi automatically during boot process. After shutdown you can disconnect keyboard, mouse and display, by what you get a very compact Internet of Things device. The hardware design around the GPIOs for this demonstration video is simple. There are 4 LEDs, 2 servos, an electric motor driven through an H-bridge, and finally 2 switches as the most simple type of a sensor. After reboot, the GPIOs can be switched through the browser interface, for example this cheap plastics laptop or a smartphone or a second Raspberry Pi can do the job. For demonstration purposes I will use a larger laptop. To get connected, simply point to the script running on my internet server and type the password you have entered during the installation process. As soon as the connection is established, you can set the variables by clicking on the control buttons. So let's turn the colored LEDs fully on. As you can see, there is a delay of several seconds between clicking the control buttons and the accordant action of the GPIOs. In a secure shell session you can see that the Perl script running on the Raspberry Pi sends the current status of the GPIOs with a 10 seconds pause to the internet server. In turn the Raspberry Pi receives the next command set to be executed if you have clicked on a control button meanwhile. Some time passes by until the connection to the server is established and the control set is received, thus the total update interval is clearly larger than 10 seconds. The second line of the status area turns green if the last instruction set has been received and executed by the Raspberry Pi. As demonstrated with the white LED, you can set the light intensity from 0 to 200, thus from off to fully on. The motor connected to the H-bridge can be controlled in the same way. The duty cycle of the pulse width signal can be set from 0 to 100%, according to a maximum value of 200. The direction of rotation is controlled by a second GPIO. That pin can be set to either low or high, thus fully off or fully on. Therewith the motor rotates either clockwise or counterclockwise. Servos are also controlled by pulse width signals, as demonstrated in my video about those devices. The pulses generated by the software are not very stable, thus you can see the servo levers oscillate around their set points. With the servos you can switch high voltage devices by simply activating their power buttons. There is no need to open the housing in order to connect your Raspberry Pi to the high voltage cabling. The poor precision of the servo pulses doesn't matter. Two switches are used as the simplest kind of a sensor. The state of those switches is displayed at the top of the browser interface. For this demonstration I have enlarged that area. The status is updated each 15 seconds or with a click on a control button. There is also a delay of up to 30 seconds until a change in state is displayed. While creating this video I had the idea to add another control button. If there is a camera module installed, you can do snapshots that are automatically transmitted to your browser. Once more there is a delay of up to 30 seconds, but it gives you an overview of what is going on at home and shows if your remote controlled Raspberry Pi is operating as intended. Since keyboard and mouse are disconnected, you can shut down your Raspberry Pi with the browser interface before unplugging the power supply. 2 C programs and 3 Perl scripts are working underneath the browser interface. Try to understand how the source code works and create your own Internet of Things with a Raspberry Pi. Learning text-based programming languages is essential if you want to become a computer expert rather than staying on the level of clicking on colored buttons. So remote control your water boiler to turn it on 5 minutes before you arrive. Water your flowers while you are on a vacation trip. See if a window or a door is open even if you are thousands of kilometers away. Drive my Curiosity Pi from any place with an internet connection. Or turn the lights off. Thanks for watching and I'll be back. R3, my camera equipped rover with a Raspberry Pi brain, got some updates. On the hardware, the communication interface with the shuttle module was modified. Up to now the connection was established using a conductive path, which has been changed to an infrared interface. The first advantage is that the error-prone mechanical parts, namely the wiper and the metal plate, are no longer in use. The second benefit is that the communication with the Atmel microcontroller is only established if Curiosity Pi faces the space shuttle. As a rover driver you will recognize the software update. Instead of transmitting single images with 20 seconds delay, you can watch a live video stream from now on. After the login procedure, some seconds pass by until the stream is established. If you can't see video images after approximately 20 seconds, you can reinitialize the connection by pressing the button Reconnect. You can also use that control button if the video stream freezes while driving the robot. As soon as the video stream appears in your browser, you can control the rover as usual. There is a lag of several seconds between clicking a control button and a visible reaction of Curiosity Pi. Remember that you are driving a robot in a distant universe that has never been mapped by satellites so far. I have tested the browser interface with Firefox and Chrome under Linux. Your browser must support MJPEG videos. While driving in my RoboSpatium, random messages are displayed in the control interface and an audio file is replayed simultaneously.
Listen to my fax machine.
If you'd like to support this project, you can make a donation and create own messages that will be forwarded to all rover drivers. Of course, driving my robots will stay free of costs, at least for you. With a donation you can help to compensate for the time and money I am spending to turn my projects into a reality that benefits free education, thus you too. You can read more about how to make a donation and get the construction details of Curiosity Pi on the project page. And of course you can have fun with driving my robots on my pages. Thanks for watching and I'll be back.
Since the Raspberry Pi is like the new Arduino, it was about time that I actually started using it. So this is the Raspberry Pi, and this is my custom board, but what does it do? Well, that's a good question. I'm about to leave to Canada, and I would like to have this computer to work for me even when I'm there, but for doing reverse engineering. But the problem is that when I crash this card, or any other card basically, well, it crashes the computer so hard that I cannot even reboot the computer. So I needed something to be able to cut the power out and put it back again. So well, we have this board here that is connected via this cable to the Raspberry Pi. Up. And then this board here is connected to, well, the motherboard here. Sorry. So you have the power switch cable, and you have the wait a sec. This, oh yeah, this one, the green one here, is the LED power indicator. So basically, this is to be able to press the button and check if the LED is on or not. And then there is this cable, which is very interesting. It is connected to like a very short ATX, I don't know, power cable that I modified. That contains here MOSFET transistor that is just cutting this green wire. So for you guys, if you know ATX, the green wire, when it's shorted with with the black wire like this one, then, well, the motherboard will start, well, not the motherboard, the ATX power supply will actually boot up and send current. So what I needed is to cut this wire here, so as a whole motherboard and, well, basically every peripheral would be, well, would lose power. So this is what I did. So from the hardware point of view, you are kind of good now. I'll post the schematics, it's already in the website. Well, so I'll boot up the Raspberry Pi. Up, wait a sec. Here we go, very simple. And here we have a website that I'm going to refresh. Well, you need to wait a bit for the Raspberry Pi to boot. Here we go. So we have welcome to the remote power management system or whatever. So we have two computers, Katao and RaBurayı. This one is this one, and Katao is, well, this one. So Katao right now has a ping, it pings, but I didn't connect all these buttons, so you should, well, it's not done yet. So for RaBurayı, which has everything, you have ATX power here that basically allows to cut the power or put it back on, or reset is just force off, force on. And then we have power switch. Press, it will press the, like, it's like emulating pressing the power switch. And force off is pressing the power switch for 10 seconds, which should force off the computer. So I'll press. So as you can see now, the power LED went on, and I indeed pressed the power switch. So we have some logs here, and here the LED is on, and we can check that. Yeah, it's running. Good. And the screen is, yeah, and now I'm gonna press again and hope. Magical. It stopped. Well, that's it for tonight. See you later.